Hello everyone, in this video we're going to be discussing what happens to the signal if it was corrupted by noise after I downsample it. So let's assume that we're given a discrete signal, and how did I know that it is discrete? Because of these dotted lines. So the dotted lines represent that the signal is repeated in the frequency domain, means that it is discrete in the time domain. And right now we're assuming that it is, in this example it is sampled by 4 kilohertz. Okay? And I'd like to reduce the sampling frequency from 4 kilohertz to 2 kilohertz. Okay? So in order to, let's first see what the signal is. Actually, this is the signal, but this is the noise. Okay? And the noise is between 1 kilohertz and 1.5 kilohertz. And the signal is band limited to 1 kilohertz. If I would like to reduce the sampling frequency, then I expect that the noise is going to corrupt the signal. Why? Because it is going to be repeated the entire band is going to be repeated every 2 kilohertz, which means that there is going to be some interference between this signal, and between the noise and this signal. Okay? Let's first take the example where we do not have where we have an ideal low-pass filter. That's basically why we need an ideal low-pass filter, so that we can filter out the noise. We pass the signal by this ideal low-pass filter, we get this signal. Okay? And remember, after I do the downsampling, then I am going to expect that the signal is going to be repeated. Okay? It's going to be repeated every 2 kilohertz. Why is that? Because that's a property of the discrete signals, that they are repeated by the same sampling frequency in the frequency domain. Okay, so the question that we would like to answer in this video is what happens if we reduce the sampling frequency and we do not have an ideal low-pass filter. And that's always the case. We never have an ideal low-pass filter. It's never sharp. Okay. So in this particular video, we're going to be assuming that it does not even exist. Okay. To take the more extreme case, we do not have an ideal low-pass filter at all, and we do not even have any low-pass filters. Okay. So the entire signal is going to pass, whether it's the noise or the signal that we're interested in. Since it is going to pass, and since we're going to be reducing the frequency from 4 to 2 kilohertz, then I'm going to expect that the signal is going to be corrupted. The noise is going to be interfering with the signal. That's the first replica of the signal, and the second replica centered at 2 kilohertz, and another replica centered at negative 2 kilohertz to indicate that I reduced the sampling frequency. And the interference is going to happen. So the noise is going to corrupt this part of the signal, and the noise is going to corrupt this part of the signal. And you expect that if the noise was already not band limited to 1.5 kilohertz, it was limited to beyond that, then you expect that the entire signal is going to be corrupted. Okay? Then the entire signal is going to be corrupted. Right? But that's not the only problem. The second problem is that the level of the noise is not going to be kept the same. The level of the noise is going to increase. Why is that? Because as you sample more, as you reduce the sampling frequency, then you're basically reducing the number of samples, which means that the spectrum of the noise is going to be increasing in the level, because the noise samples have to accumulate on a lower number of samples. Okay? So if you have, let's say, 10 samples and you want to reduce them to 5 samples only, the power has to be kept the same according to Parseval's theorem, which means that those 5 samples have to accumulate the entire power of the noise of the 10 samples, which means that each one sample is going to have an increased value of amplitude, and that's why the noise level increases. But remember, as long as the SNR, which is the signal level to the noise level, is kept above a certain threshold that depends from an application to the other, and let's assume that that level for our application is 10, okay, then as long as this the new SNR is above that level, then you're going to claim that I'm satisfied with that. So I can reduce the sampling frequency up till the point that the SNR hits the 10. Okay? As long as it hits the 10, then I'm going to be satisfied with that. And remember that the noise level increases only since the noise is random. Okay? The signal's level is kept the same. The signal's level does not reduce, is not increased, and that's why the SNR is kept the same. Why? Because the signal level is basically a non-random signal. Okay, so let's calculate the value of the SNR. How do we find the value of the SNR? The value of the SNR is equal to the signal amplitude over the noise floor. And remember, I'm using the notation of the SNR here. It is usually the SNR means signal to noise ratio, and it usually means signal power over noise power. But here I'm going to be using the notation. I mean it to be signal amplitude over the noise amplitude. Okay, so that's amplitude, not power. Okay, and if you would like to calculate it in dBs, then you take the log and multiply by 10 and multiply by 20. And if you'd like to calculate, if you're given the SNR in dBs and you want to calculate the linear, then you divide by 20 and raise it to the 10. Okay. Okay. So how do we do the math? How do we get, if we're given a problem, how do I calculate the lowest sampling frequency that I could achieve? Well, it all depends on the noise floor that you could achieve. If you have a particular SNR, the signal amplitude is going to be kept the same when you reduce the sampling frequency. The noise floor is what is going to deteriorate. Is going to increase basically. Okay? And that's why the SNR is going to deteriorate. Okay? So the noise floor over the noise floor as NF1 over NF2 is equal to the reciprocal of the sampling frequency under the square root. Okay? So let's take an example. Okay? If you are given 10 kilohertz of sampling frequency and the signal that you have is 20 millivolts per hertz, that's the amplitude, maximum amplitude of the signal, and the noise level is equal to 0.5 millivolts per hertz. That's the noise. Okay? And it is a discrete signal. Okay? Discrete system. Why? Because they told me the problem tells that the FS1, the sampling frequency is 10 kilohertz. Okay? So I'd like to find what the value of the frequency that I would like to, the minimum frequency that I could attain that keeps the noise floor 20 dBs below the signal level. Okay, so if you're given a signal level, the noise floor is going to increase. Okay, as long as this is 20 dBs, okay, then I'm satisfied with that. Okay, what is 20 dBs? 20 dBs is basically 10 power 20 over 20. Okay, which is equal to this value is when you do the math and you do the SNR. So remember that the SNR, I put the signal over the noise. Okay, the signal power, the signal amplitude over the noise floor. Okay, the signal amplitude is going to be after the value of the after reducing the sampling frequency is going to be kept the same, and the SNR that I would like to attain is 10 power 20 over 20. Okay, which is equal to 10. Okay, so the noise floor has to be equal to 2 millivolts per hertz at most. Okay, so that's the maximum value of the noise floor. Okay, remember that this calculation is done after we do the sampling reduction of sampling frequency. Okay, so right now I can substitute in the formula NF1 over NF2 is equal to the reciprocal of the sampling frequencies the ratios of the sampling frequencies under the square root. Okay, and here I have a mistake. Okay, that's 5/8 kilohertz. Okay, remember that the main concept that we're trying to achieve in this video is that you can reduce the sampling frequency, but up to a certain value only. You cannot reduce it indefinitely. Okay, and the reason is because reducing the sampling frequency increases the noise level and thus reduces the signal to noise ratio. Okay, so I hope this helps, and let me know if you have any questions. And remember that this document is in the description of the video below, and the Arabic version of this video is in the description of the video below as well.